Hey guys, in this video we're going to talk about the perpendicular, first of all, what a perpendicular bisector is, and then we're going to talk about the perpendicular bisector theorem. So, first of all, what is a perpendicular bisector? Well, a perpendicular bisector is a segment, ray, or line that bisects a segment at a 90-degree angle at its midpoint. So when we talk about perpendicular, if you guys remember what perpendicular means that we have two lines, rays, segments that intersect at a 90-degree angle. So then we've got the perpendicular element here, the 90-degree angle. Then we have the bisector element. So if I've got a segment, and the reason I say segment is because if we're going to bisect something, we're basically going to be cutting it in half. And if we have a line or a ray or anything else that's infinite, we can't take half of infinity. So the only measurable object we can really bisect besides an angle is a segment for our purposes in this class. So if I've got a segment and this segment has a midpoint right here, and I'm going to put my tick marks there. If you remember, those tick marks mean congruent. So for example, if this is segment AB, M is my midpoint, that means that it's right in the center of the segment. So a bisector is any line, by definition, ray or segment, that cuts through that midpoint. So I could have a ray pass through the line. You can see that ray passes through the midpoint, so this is a bisector. I could have another segment pass through. You can see this segment also, if I could draw, goes through the midpoint. I could have a line pass through. That's also a bisector. So bisecting just has to do with going through the middle and cutting in half. And for a segment, that's through the midpoint. So if we combine these guys, we've got perpendicular and bisector. What that means is when I have a segment, so I'm going to draw a brand new segment here. When I've got a segment and I have a midpoint for that segment, I know that that's right in the middle. If I were to draw a perpendicular bisector, that means I have to draw a segment, line, or ray that not only goes through this midpoint, but also goes through the midpoint and intersects that segment at a 90-degree angle. That is why it's called a perpendicular, that's the 90-degree element, bisector, that's the bisecting element, cutting it in half. So that's what a perpendicular bisector is. It is a segment, line, or ray that cuts another segment in half. Now we have a theorem called the perpendicular bisector theorem. So I'm going to scroll up here. No, I'm not actually. I'm going to try to scroll up here. So let's look at the perpendicular bisector theorem. So we know what a perpendicular bisector is now. A perpendicular bisector is a line, segment, or ray that bisects a segment, cuts a segment in half at a 90-degree angle. So what is the perpendicular bisector? Let me add this on there. Theorem. Okay. The perpendicular bisector theorem has to do with the points that actually lie on that perpendicular bisector. So let's draw our picture again. I'm going to draw a segment. And I'm going to call this segment CD. Okay. I'm going to draw my midpoint for my segment, put it in the middle, put my little marks to show that those are equal congruent segments. CM is in fact congruent to MD. So I'm going to draw the perpendicular bisector. So this is going to pass straight through at a 90-degree angle. And I'm going to make this a line. Oops, not that kind of line. Oops. So I'm going to make this a line. And I'm going to put little arrows on there to indicate that this is actually a line. And the reason I'm going to do that is because I kind of want to establish the idea that it keeps going. So what's up with this perpendicular bisector theorem? Well, the perpendicular bisector theorem states basically any point that you pick that is on that perpendicular bisector is going to be the same distance away from each endpoint. So basically this segment and this segment are congruent. So let's say that's point R. That means that CR is congruent to RD because R is on the perpendicular bisector. So by that token, any point that I draw on the perpendicular bisector is also going to follow that pattern. So let's pick another one. Let's say I drew a point all the way down here. Let's call that point J. Well, since J is on the perpendicular bisector, that means that J is the same distance from D as it is from C. So that means that we now also know that JC, segment JC, is congruent to segment JD. You kind of get the idea. And this will work with any point I put on this line. I could put a point here. And this one would be the same. I could put a point here, and this one would be the same. So basically that's what the perpendicular bisector theorem is saying. So how can we apply this to some of the problems that we've looked at in the class? Well, let me draw another segment. So you may see something like this, and we'll call this LA, because the Rams are playing in the Super Bowl. So we'll call this LA, and we'll draw the midpoint here. So LM is congruent to LA, and we're going to draw the perpendicular bisector. And again, this can be a line segment array, but I'm making it a line. And then I'm going to put a point here, R, and I'm going to connect these two. So there's a couple of things that you might see in one of the assignments. First one is, let's say I tell you that RA equals 12. Now, do you notice how when I say RA equals 12, there's no symbol above it? Yet over here, these are symbols. That's because here we're talking about the objects themselves. A segment is the same length as a segment. Over here, I'm actually talking about the exact measure. We're not talking about the object itself. We're talking about the measurement. It would be the difference between, let's say, you're driving from San Marcos to Austin. Well, how do you get from San Marcos to Austin? Well, you drive on I-35. So I-35 would be the object, right? And then how far did you drive to get there? 25 miles. So I-35 is the actual object you're traveling on. That would be the segments over here. These are objects. 25 miles would be the actual length or measurement of the object, which is why you have the RA equals 12. There's nothing above it. So the question is, if RA equals 12, what's RL? Well, this should be pretty simple. Since this is a perpendicular bisector, we know that this and this have to be the same because R has to be the same distance from A as it is from L. So boom, real simple, RL is 12. So that's one way that we have applied the perpendicular bisector theorem. And I'm trying to get my screen to move, so give me just a minute. It's being a little fussy. Back, I got my screen to move, so I'm going to go ahead and erase this section here, since we've already seen it, and give you another example of something you might see on the assignment. So let's draw our segment again. So I'm going to draw my segment, and I'm going to call this LA, just like the other one. And I'm going to put my midpoint in the middle, and I'm going to mark these two congruent. And then I'm going to draw my perpendicular bisector. And again, if I could draw a perpendicular bisector, remember, is a line segment or ray that intersects a segment at its midpoint. So here's another thing you might see. You might see a point on there. We'll call that C. And you may say that C is 2x plus 4, and LC is 5x minus 7. And it may ask you to solve basically for two things. It may ask you to solve for x, or it may actually want you to find the length of these two segments. And remember, they're equal. We know these two guys are equal because C is where? It's on the perpendicular bisector, so it's the same distance from L as it is from A. So let's solve this. Well, that means I know that 5x minus 7 has to be the same length as 2x plus 4. So I'm just going to set these guys equal to each other and solve this algebraically. So I'm going to subtract the 2x from each side. So I'm going to have 3x minus 7 equals 4. And then I'm going to add 7 to both sides. And I'll come up over here because we're running out of room. So the 3x came down. That plus and minus 7 cancels, and that gives me 11. So then I'm going to divide both sides by 3. So x equals 11/3, which is a very ugly number, which if I actually did that in the calculator, I get about 3.7, something like that. Okay? So then the question is, well, how would I find CL and CA? Well, I would take my 3.7 and I would just plug it in for x. And I could plug it into that one, or I could plug it into that one, because what do we know? They're both the same, right? So let me pick the 2x plus 4. So 2 times x, which we figured out was 3.7, plus 4 is the length. So that's going to be 7.4 plus 4, which is 11.4. So that's how long each side is. And if you want to verify you got the right answer, let's try 5x plus 7. So let's minus 7. So 5 times 3.7 minus 7. So 5 times 3.7 is 15, is 18.5. Minus 7 gives you 11.5. Now, these aren't exactly equal because we rounded, we approximated. Had I plugged in 11/3, I would have gotten the exact same answers for both of them. But this is an example of why we try not to round and approximate to decimals, especially when we're doing radicals, if we don't have to, because it makes the answers not quite as accurate. So anyway, this is the perpendicular bisector theorem and how we use it.